was just saying a little bit about the origins of the company, that everything started in the late 1980s when our founders found out that you can predict the movement of photons in tissue, originally done in breast cancer imaging. Now, mostly we specialize in brain imaging using this exact technology. And here you can actually see a screenshot of the first patent that they submitted. And yeah, so companies really started in the 1990s, and throughout the last 25 years, we've been really interested in pushing neuroimaging, specifically using FNIRs, developing new systems. You can kind of see where we started with these fridge-sized systems. Now we are making the system smaller and better, more portable to really enable naturalistic neuroscience. So really bringing imaging into everyday scenarios, real interactions, for example, real setups. And this is very important to us. And one big step was last year we merged with another FNIRs company in the summer. They really focus on, let's say, making the systems as small, as easy to use, and as portable as possible. Whereas we at NIRx with NIRx in Berlin, we're still trying to really, let's say, push the boundaries of what's possible so that we can now together, really help all of the researchers in all of the fields adopt this technology. Yeah, we currently have over 1,500 active end users worldwide, with the community steadily growing. And maybe about myself. So I have originally a background in clinical psychology, so I strayed a little bit far from where I've come from. But I do have quite a bit of experience in EEG, which is what I used in my research, mostly EEG and eye tracking. But then about 3 years ago, I switched to NIRx because I saw a lot of potential in the technique. And I think it's a very exciting field, a field where there's still a lot left to explore. And usually now I like to do a little introduction round. I didn't know how many people we were expecting today, so maybe we can just do a quick show of hands. I would just like to know who of you has heard of FNIRs before and knows what FNIRs is and how it works. Okay, 2 people. Okay, so we have some work to do, so that's good. I'm glad I didn't skip the introduction into what the technology is. My next question would have been if you've used FNIRs before, but since few people have experience with it, I don't know. Soros, did you use it before, or you've seen it, or have you used it yourself?
Yeah, we used it for dynamic recordings.
Right. Okay, so for hyperscanning. Very nice. Okay. Wonderful. Then for today, so I was a little bit ambitious. We will see how much time we have. I want to start with FNIRs fundamentals, so giving you a quick introduction into the technology and how it works. Then going over to more advanced topics. Specifically, I want to put a focus on high-density FNIRs, so really pushing what's possible in terms of the spatial resolution of the technology. And then SPA FNIRs, where researchers, so we love abbreviations, systemic physiology augmented FNIRs is what it's called. And this is also what I want to show you in a live demonstration. I have a system here with me for a whole head setup with systemic physiology. If we have some extra time at the end, we can also look at multimodal FNIRs, because FNIRs is actually very well suited to be integrated with other neuroimaging modalities like EEG or fMRI, and also with neuromodulation such as TMS or TES. Just due to how the technology works, it's very friendly towards other technologies. Okay, and if you have any questions, please feel free to just raise your hand and let me know. And as I said, so I'm kind of trying to show you everything that's possible today with FNIRs. Of course, it's very ambitious because there is a lot that's possible. So it's going to be more of a high-level overview. But if you ever have any questions, want to discuss anything more in detail, feel free to come up to me afterwards, or also we could meet anytime online if you have any questions. Okay, let's start with the fundamentals. What is FNIRs? How does it work? So FNIRs is also an abbreviation, of course, stands for Functional Near-Infrared Spectroscopy. As says in the name, we're measuring functional activation of the brain. So we do not do structural imaging in FNIRs, that is not possible, but we're measuring functional activation, network activation, activation due to different tasks, for example. And for this, we use near-infrared light. Why do we use near-infrared light? Well, probably maybe when we were children, every one of us tried this little experiment here where we shine a white light through our tissue. And you will observe in this moment that only the red light passes through on the other side. That's because human tissue is very good at letting through longer wavelengths, such as red light. And if we look at the complete spectrum of wavelengths, of light and radiation, we can see that we're right at the edge of the visible light spectrum. That's where we operate with FNIRs. Because at this part of the spectrum, we have a window. It's called the optical window. This is pretty much what all FNIRs devices that do continuous wave FNIRs, which is the type of FNIRs that we do. There are other types too. The type of FNIRs we do, continuous wave FNIRs, uses wavelengths from this spectrum. You can't see it as well here, but it is marked on the graph. It's between 700 and 900 nanometers. We use the light here because the light passes through the tissue, and within the tissue, in this window, there are specifically two molecules that absorb this light very strongly, which is oxygenated and deoxygenated hemoglobin. Higher wavelengths, you can see, would also pass well through the tissue, but we have absorption going up in other molecules that are very commonly found in the tissue, such as water. So that's why we use wavelengths from this optical window to wavelengths, because with FNIRs, we're interested in two measures, oxygenated and deoxygenated hemoglobin, and we can extract both from our measurements. That's why we're using two wavelengths. There are also FNIRs approaches with which you can use more wavelengths and then try to resolve for different molecules in the tissue. This is all concerning FNIRs, continuous wave FNIRs, as we call it. Yeah, so infrared light of these specific wavelengths. And now, what happens if we put this light into the tissue? What happens is what you can see here. So this is what we call scattering. So we put an infrared light source on the head, and the photons scatter into all directions. We have more photons close to the light source, and this kind of fizzles out. So this is a very important concept, because now if we place a detector in proximity to the source, to the light source over there, we will see that, or we can prove through so-called photon migration simulations, something that comes from the physics world, we can show that most of the light that is being detected here at the detector site followed this path that is marked here. So you can see the light enters through the skin, through the skull, cerebrospinal fluid, into the cortex, and back out on the other side. Yeah, so this is how you can kind of picture it in this curved path. It's also called a photon banana, if you want to make it a little bit more intuitive. So yeah, and so the light passes through, and in between here, it is scattered. That's why we see this pattern, and it is being absorbed. Again, by different molecules, primarily the two wavelengths we're using, by oxy and deoxyhemoglobin. So by looking essentially how much light comes back out at the detector site, we can tell how much oxy and deoxyhemoglobin is in this path between the source and the detector, depending on how strongly the light was absorbed. There's a little bit of math involved as well. I'm going to skip that today. It's built into most FNIRs analysis software, though. And then, of course, with FNIRs, we can do a single channel, can be done in certain clinical applications. For example, if you look at traumatic brain injury patients or babies, things like this. But typically how it looks is that we're placing a lot of sources and detectors over the whole head. Because FNIRS is quite location specific, so the light can only travel so far, meaning that exactly where the light passes through, that's where we're measuring. So depending on which brain region we're interested in, that's where we should place our sensors so that we measure the oxygenation specifically in this brain region. And yeah, so this you can see, and you can also cover different brain regions, of course. If you have teacher-learner interactions, if you have, for example, someone who is doing motor rehabilitation, you might be more interested in primary motor cortex, somatosensory areas. So it's really flexible that way. Today, I will show you something more like this, so more of kind of like the whole head setup, which is, for example, something that you would want for connectivity measures, for example, or for network measures. And then this part I probably don't need to explain. I think you're all familiar with this. So the underlying signal that we're looking at in FNIRS is a hemodynamic response. Important thing here just to remember is that we are kind of bound to the same principles that we are when we measure with fMRI. For example, we're measuring the hemodynamic response, which is slow. It's a physiological process, takes a couple seconds to go into effect, and also a couple seconds to return to baseline after the stimulus presentation. So it's not a direct measure of brain activity, it is an indirect measure of brain activity. But that in itself can yield, of course, more interesting questions, as you probably know. And then we can, you can see kind of this is kind of what the raw signal would look like, and then we can project all of this because, again, we know where the sensors were placed onto the cortex. So this is, for example, an activation map that resulted from a finger tapping task with the right hand. One more important concept to keep in mind is the source detector distance. This is going to also be important once I talk about the high density FNIRS. Source detector distance is important because how far I'm placing my sources and detectors determines how deep the light goes into the tissue. So there is a maximum with FNIRS, meaning if I place a source here, a detector here, the detector is not going to see any of the light that comes from the source, because you should saw it yourself. If I go back here, the light only spreads so far. We cannot put more light into the tissue because we don't want the tissue to heat up. So with FNIRS, it's very important. It is a technology that is limited to cortical areas. So we cannot record subcortical activity and deeper brain structures. Yeah, so that is important. Typically in standard FNIRS setups, we're somewhere around 30 to 35 millimeters. Then what's also important, though, to keep in mind is that shorter distances will result in the light not going as deep and staying more superficial. This will be important when we talk about the next concept. And then again, to kind of show you, so this is what a raw signal would look like. So we have time course. It's more similar to EEG rather than what we look at in fMRI, but we have a time course. We have two curves per channel. So one channel, also important concept. A channel is always the pairing of the light source and the light detector. So we have two time courses per channel, which display one for the one wavelength, the second for the second wavelength, and it's light intensity in millivolts. So you can see how much light is arriving at the detector. It's a millivolt measure, which we then take with a little bit of math. We convert it to oxygenated and deoxygenated hemoglobin concentration. And as per usual, when we talk about neuroimaging, we have to also talk about artifacts. So FNIRS is not free of this. Every neuroimaging modality deals with its own artifact types. In FNIRS, one that is very, very important to consider is physiology. So Our beautiful HRF that we have over there, it takes a little bit to get there because the raw FNIRS signal has a lot of physiology in it. Because of course, physiology, it changes the concentration of oxygen in our blood, right? Things like the heartbeat, respiration, blood pressure, all of these influences. So if we look at the raw FNIRS signal, we don't only have kind of what we're most interested in, which is the evoked cerebral response that's neuronal in origin, but we also have a bunch of systemic noise and of course also non-evoked. So we have two ways to deal with this in FNIRS. The first and the more common one, let's say that more people are, let's say, using as a default these days, are short distance detectors. It's exactly what the name says. We're placing a tiny little detector very close to the source so that the light only passes through the extracerebral layers of the tissue. And then later on, we remove this from our raw signal, leaving us with only the brain activity. Some researchers go even further and they record for peripheral physiology, which is also something that we will talk about today. That's this systemic physiology augmented FNIRS that we're talking about. So you can record physiology in addition and then see kind of to disentangle how much is still left in the FNIRS signal after we've removed the short distance detector signal. Okay. So yeah, to summarize this part, with FNIRS, we're measuring hemodynamics. In our case, both oxygenated and deoxygenated hemoglobin concentration changes at a fairly high temporal resolution. So this is something I haven't mentioned yet. With FNIRS, we're mostly, let's say, somewhere around 10 Hertz. We can go up to 20. So we can get a really good impression of the shape of the hemodynamic response function. It is, however, only for cortical structures, no deep structures. It's a relative measure. We're not getting absolute hemoglobin with this system. Again, there are other types of FNIRS, time domain or frequency domain FNIRS that try to get the total hemoglobin or the absolute hemoglobin values. But of course, why are we not doing this? Because it's technologically a lot more difficult to do. Yeah, and very important, FNIRS contains systemic physiology. So this is something that we have to consider when we set up our experiments. There are a lot more resources. If you like, I can provide these slides afterwards for everyone to share. But there is a really, really nice review from 2014, this one, really on the instrumentation and methodology. And then there is a best practices paper, not too old, from 5 years ago, that really goes into what should you consider when you design an experiment, what needs to be included, what should your measurement look like. So these are the two that I would recommend everyone who's interested to read. Anyone have any questions so far, or was it clear?
This banana shape, is it like 3D?
Yes.
So you put a ring around. How does that for you?
Yeah. So you can kind of picture it maybe a little bit. If we look at a cap, so kind of on our caps, I can show this a little bit better on the slide so everyone can see it. That was too far. Yeah. So here you can see kind of this connector. We put it to keep the connection, let's say stable and limited to 3 centimeters. But this is where you can kind of picture this light going through. So all the light that goes to, so sources for us are always red because infrared detectors are blue. So this is kind of where you can picture the light going through underneath in this kind of banana shape. So it really does look like in 3D, like banana.
But it's not like a ring.
No, exactly. It really only goes like into the tissue and back out on the other side. So it's this part of the circle.
Go the opposite direction as well?
It goes also in the other direction. So you can see here, for example, so the light comes from this source. Sorry, I think I misunderstood, but yeah, so the light goes out here and it goes into all directions. Exactly. So it scatters everywhere, which is why we create these these kind of arrays that allow us to cover the whole cortex. Exactly. And when one source fires, these 4 detectors would see the light. Very good question. Okay. Any other questions? Okay. Then I will move on very quickly with a little comparison, because we love comparisons. But just to show you in what cases, for example, FNIRs can be useful. So I think we are all aware that, for example, fMRI, it is just the gold standard of neuroimaging in terms of the spatial resolution. There's no doubt about that. So why would we need FNIRs? So FNIRs really comes in at, let's say, like a critical point where with FNIRs we have a modality that is completely mobile and wireless, meaning we can use it in very naturalistic settings. We can take our experiments from the fMRI, we can bring them outside of the scanner, we can have a similar measure, and we can really assess, okay, is what we're measuring in the fMRI, does it also apply outside? Also, we do have the higher temporal resolution, higher spatial resolution than, for example, an EEG. We have the two different chromophores, oxy and deoxyhemoglobin, which can also help us pick apart some factors when it comes to neurovascular coupling. We also, very important, we don't have any contraindications for the imaging modality. So it is a modality that's solely based on light, meaning that, the light is in a range where it's completely eye safe, there's nothing you need to worry about, no interference with other electrical devices. So it really comes in at a point where we can be very exclusive, we can make our experiments very naturalistic, and again, it is portable. It is mostly categorized as being more portable than EEG because it's more robust to motion artifacts. So it is a very nice, let's say, it comes in a niche where neither EEG nor fMRI are able to provide us with the same information that FNIRs can. And accordingly, it is being used in a lot of different contexts. I already talked about a few of these a little bit. We do see a lot of use, especially in clinical populations, because it is very fast to apply, as I will hopefully be able to show you. We don't need gel. It is solely based on contact of the optodes with the scalp, so very fast to set up, saves us a lot of time. It is used very much in neurorehabilitation, so anything that has to do with movement. Also, the area of social neuroscience, we will come to it a little bit later. So people interacting with each other, it's a big topic in FNIRs. Also, we use it for BCIs. We use it for attention, concentration in combination with other modalities as well. So it has a lot of different applications.